What if I told you your database queries are probably running 100 times slower than they need to be? Yeah, that's not an exaggeration. We're talking about taking seconds, even minutes, when it should be milliseconds. Think about it. Every slow load time, every unresponsive app often points back to a database struggling to find data. This isn't just annoying, it costs businesses millions and frustrates users to no end. Today, we're cutting through the noise to show you exactly how database indexes supercharge your queries, making your apps feel snappy and responsive. By the end of this video, you'll know how to identify bottlenecks, design effective indexes, and finally stop guessing why your queries are crawling. The blind search, full table scans. Okay, so imagine you're looking for a specific paragraph in a massive, unindexed textbook. What do? You start page 1, read every single word until you hopefully stumble upon what you need. That, my friends, is a full table scan in a nutshell. The problem isn't just theoretical, it's a real performance killer. On a table with a few hundred rows, you might not notice. But scale that up to millions or even billions, and your query time explodes. Your users are staring at spinners, and honestly, who wants that? Real talk. I've seen devs spend days trying to optimize application code, only to find the core issue was a missing index on a critical database column. It's like trying to make a car go faster by polishing the hood when the engine's seized. It's frustrating because the solution is often so simple, yet overlooked. Your database's cheat sheet, the index concept. Okay, so if a full table scan is like reading every page, an index is like the index at the back of that textbook. You want to find B trees? You go to the index, find B trees, see page 247, and jump straight there. No endless flipping. Databases do the exact same thing, often using something called a B-tree data structure. Not all indexes are created equal, though. You've got your primary key indexes, which are often clustered, meaning the actual data rows are physically stored in the order of the index. Then there are unique indexes, ensuring no duplicate values. And finally, just plain old non-unique indexes, perfect for speeding up comment or clauses. The real magic is that indexes take your query from an linear scan to an logarithmic search. That means as your data grows, the performance impact of a well-indexed query barely budges. Wild, right? Instead of proportional slowdown, you get near constant time for lookups. That's a game changer. The double-edged sword, indexing's hidden costs. Here's the deal. Indexes aren't free. Every time you insert, update, or delete a row in your table, the database also has to update any associated indexes. This means more I/O operations, more CPU cycles, and ultimately, slower write performance. So if your application is write-heavy, you need to be strategic. Still with me? We've covered the why and what of indexes. Now let's dive into the how, crafting indexes that actually make a difference and avoid those sneaky performance traps. This is where you go from guessing to genuinely optimizing your database. Another cost? Storage. Indexes are essentially separate copies of your data, organized differently. For a table with millions of rows, an index can easily take up as much or even more disk space than the actual data itself. So, you're trading disk space for speed. It's a classic engineering trade-off. So, when should you not use an index? Honestly, if your table is small, say, less than a few thousand rows, the overhead of maintaining an index might outweigh the benefits. Also, if a column has very few unique values, like a booleans_active flag, an index won't help much because the database will still have to scan half the table anyway. It's about selectivity, which we'll get to. Crafting the perfect index, strategy, not guesswork. Okay, so you know what an index is and its costs. Now, how do you build a good one? First, consider single column versus composite indexes. A single column index is obvious, but composite indexes, which use multiple columns, are where things get interesting. The order of columns in a composite index matters a lot. If your query filters by column_A, then column_B, your index should be column_A, column_B, not the other way around. Next up, selectivity. This is crucial. An index is only useful if it narrows down the search space significantly. A highly selective column has many unique values, like an email address. A low selectivity column, like our is_active boolean, won't help much. Aim for columns in your where clauses that filter out a large percentage of rows. Plot twist. You don't have to guess if your index is actually helping. Every major database has an explain command or similar that shows you the query plan. It tells you exactly how the database intends to execute your query. If it's using an index, which one, or if it's doing that dreaded full table scan. This is your secret weapon for optimization, seriously. Beyond the basics, advanced indexing and my take. Let's talk about some advanced moves. Partial indexes, like in PostgreSQL, only index a subset of rows that meet a certain condition. Super useful for large tables where only a small fraction of rows are actively queried. Then there are covering indexes, which include all the columns needed by a query, so the database doesn't even need to touch the actual table data. That's pure speed. My personal indexing philosophy boils down to this. Start without indexes where you can, then add them only when you identify a performance bottleneck. Don't just slap an index on every foreign key. That's a common mistake I see. Use explain to confirm your assumptions. It's an iterative process, not a one-time setup. Hot take. The default indexes databases create for you, like on primary keys, are often enough for 80% of your needs. Don't overthink it initially. Focus on understanding your actual query patterns, not just what you think they might be. Over-indexing can be worse than under-indexing because it masks the true bottlenecks and adds unnecessary overhead. Let's recap. Full table scans are slow and resource-intensive, especially for large datasets. Indexes like B-trees provide logarithmic time complexity for lookups, drastically speeding up queries. Indexes come with costs, increased write performance overhead, and additional storage space. Effective indexing requires strategy, understanding composite indexes, selectivity, and using explain to analyze query plans. Advanced techniques like partial and covering indexes offer more granular control and performance gains. The key takeaways: don't guess. Use explain to understand your query performance. Index strategically. Prioritize columns used in where clauses, join conditions, and order by clauses. Avoid over-indexing, especially on small tables or low cardinality columns, as it can hurt more than help. Regularly review and adjust your indexes as your application's data and query patterns evolve. If this helped you understand something new, consider supporting the channel. Every bit helps keep these videos free for everyone. Drop a comment with your thoughts on indexing or share your own database war stories below. I genuinely love hearing from you all.